we have been discussing the mathematics of operators, right? So in the context of mathematics of operators, it is very important for us to establish what an eigenvalue equation is. So for any operator A, right, there is an eigenvalue equation that says that A acting on a set of, let us say, kets psi equals A times psi, right? So this is the eigenvalue equation. This is the eigenket, and this is the eigenvalue. Okay. So if A is a matrix, if I write it in a matrix form, I will call this an eigenvector and eigenvalue, right? Now I want to talk about what happens if you have two operators. So operators are deeply connected to the process of measurement, as we will talk about in the postulates of quantum mechanics starting tomorrow. Excuse me. So I want to talk about what happens when you have two operators. So if you have forgotten, it might be a good time today to go back and revise what we discussed in the very first lecture about sequential Stern-Gerlach experiments. Okay, so we will make a connection with whatever I'm talking about to the sequential Stern-Gerlach experiments when we talk about the postulates of quantum mechanics. So let us say that you have another operator B. Okay, another operator B. A and B are two distinct operators. Okay. Now let me take two cases. Case one, consider another operator B. Okay. Now, case one. The first case is the operator A and the operator B commute. Oops. A, B equal to 0. This means that the two operators commute. Okay, what is the meaning of this? I'm sure you know this from the mathematics of matrices. This means the symbol A comma B within square brackets simply means AB minus BA. Okay. Now notice that the ordering of operators matters. In other words, suppose if I have some vector alpha and I want to know what is the action of AB on this vector alpha, the way I would do this is I will first act B on the vector alpha. So I'll act B on alpha. Okay, and this will give me a new vector B times alpha, which is some beta. Okay, and then I will act A on this new vector beta, and I will get some other vector beta prime. Okay. Suppose if I want to know the action of BA on alpha, then I will first act A on alpha. I'll first act A on alpha, right? And then I will get some vector alpha prime. Now I will act B on this alpha prime, and then I will get some other vector gamma, right? So the result of the first operation gives me a vector, some beta prime, and the result of the second operation gives me another vector gamma. And in general, the vector beta prime and the vector gamma are not the same vectors. But it could happen that the vector beta prime and vector gamma are the same vectors for certain special classes of operators. For some special classes of operators, it might turn out that the order in which you act the operator on the kets does not matter. Okay. In other words, the operators commute. If AB minus BA equal to 0, remember that this is an operator equation. If I say AB minus BA equal to 0, this is an operator equation. This has to be understood in the following sense. In the linear vector space, if I take AB and act it on any vector alpha, this is the same as BA acting on the vector alpha. Because as I've emphasized repeatedly, operator by itself is meaningless. Only the action of operator on the kets takes a specific meaning. Okay. So this is what commuting operators mean. Now there is actually very interesting fact about commuting operators, and this relates to their eigenkets and eigenvalues. So that is what we started this lecture with. We started by saying that consider the vector A that has, operator A that has some eigenket psi. Okay. Now it turns out that if A and B commute, they have a common set of eigenkets. If two operators A and B commute, they have a common set of eigenvectors. Now remember that I'm not saying anything about eigenvalues. The eigenvalues of A and the eigenvalues of B themselves could be very different, but the eigenvectors could be the same. So what does this mean? So let us say that I have some operator A, okay? And then this has, let us say, a set of eigenvectors phi n corresponding to eigenvalues a n. Okay, this is the eigenvalue equation for the operator A. Okay. Now, these are all the eigenvectors of the operator A. There is nothing else. Okay, suppose if you give me some other eigenket saying that no, this is also an eigenvector, I'll say that no, this corresponds to one of the phi n's. Okay, so I have solved for the eigenkets of A. If I have the matrix form of A, I'm simply saying that I know all the eigenvectors of A. If A is a 3 by 3 matrix, I know all three eigenvectors of A and all three eigenvalues that each eigenvector corresponds to. Now along comes another operator B, okay? And let us say that B and A commute. So now let me act B on both sides of this equation. So B acting on A phi n. Now an is just a number, so I can pull it outside because these are linear operators. B acting on phi n. Okay. Now, since A and B commute, on the left hand side, it doesn't matter if I write BA acting on phi n or AB acting on phi n. Since AB equals AB minus BA equal to 0, I can write the left hand side. I can write the above equation as AB acting on phi n equals AN B acting on phi n. Okay, because the order does not matter because A and B do commute. Now look at this equation closely. B acting on phi n is going to give me some vector, whatever that vector is. Okay, so I can write this equation as A acting on the vector B phi n, because this combination B acting on phi n is a vector, equals AN acting on the combination B phi n. Okay, so please follow closely because these steps are important. These manipulations might seem a little easy, but every step is important. So the operator A acting on the combination B phi n equals the eigenvalue AN times the vector B phi n. But this means that the vector B acting on phi n is an eigenvector of A, eigenket of A with an eigenvalue an. So this implies that B phi n is an eigenket of A with eigenvalue an. Now this can be surprising because we started by saying that we have solved for all the eigenkets of the operator A and these correspond to phi n. So if A is a 3 by 3 matrix, I know all three eigenvectors. Now after this set of manipulations, we find that there is a new eigenvector of A, B phi n. So the only way to reconcile both these statements is by claiming that the vector B phi n, which we claim to be an eigenket of A, is not a new eigenket, but it is actually phi n itself. In other words, this implies that B phi n, which is an eigenket of A, has to be proportional to phi n itself. That is the only way in which B phi n can be an eigenket of A, because we know that the eigenkets of A are phi n's. Now B phi n doesn't have to be equal to phi. Why? Because B phi n can be 25 times phi n, because if you substitute 25 times phi n in the above equation, the 25 cancels on both sides. So B phi n should be at most proportional to phi n. So let's say that the proportionality constant is some number. So let's call this B phi n equals some Bn times phi n. Okay. But if you stare at this equation, you will recognize that this is nothing but the eigenvalue equation for the operator B. The operator B, which commutes with the operator A, has a set of eigenvalues Bn and a set of eigenkets which are the same as the eigenkets of A. So we prove the statement that if A, B equal to 0, then they have a common set of eigenkets. Okay. This is a very important statement in the context of quantum mechanics, and we will discuss the importance of this statement as we go along in the next few lectures. Okay. Are there any questions about this? Okay. So before I move on to the second case, obviously case number 1 is what happens if two operators commute. The second case obviously is what happens if they do not commute. But before I move on to that case, I have to tell you a little bit about some statistics. Okay. And I'm sure many of you know this already, but let us put this as an aside for people who might need a refresher, like me, because I always keep forgetting basics of probability theory. So let's go through some very basics of measurements. Like, for example, what is an average value? Well, suppose, there is a very good example in the textbook by Griffiths that I've taken. This is a very simple example, and this is more than enough to illustrate my point. So suppose if you have a bunch of people in a room, okay, and each corresponding to a different age, okay. So let us say that there is a set of people in a room with different ages, age groups. Okay. So let us say that let us call this age as the number j. Okay. So when I say that I'm talking about n of j, I mean that this is the number of people with age j in that room. Okay. So let us say n of 24. So somebody is asking me, sir, please repeat why B operating on phi n cannot be equal to phi n. Okay. All right. So let us go back here. So I have the equation A acting on B phi n equals an acting on B phi n. Okay, and the claim is that this means that B phi n has to be proportional to phi n, and the proportionality constant can be anything. So I said that this has to be B phi n equals some Bn phi n, right? And the question is, why is B phi n not just equal to phi n? Why do you need a proportionality constant there? Whenever you solve for an equation, you have to solve for the most general solution. So suppose if B phi n is 37.5 times phi n, okay, take some ridiculous number. Now, all I have to make sure is that this equation is satisfied. So substitute this over here. What happens? A acting on 37.5 phi n equals an times 37.5 phi n, and the 37.5 conveniently cancels on both sides, and I have a phi n equals an phi n, which is the eigenvalue equation. Okay, so the most general solution for this equation is not b phi. No, b phi n could very well be equal to phi n, but that is just one possibility. Okay, this number need not be just one, it could be anything. And no matter what this number is, the equation which I have underlined is always solved because the proportionality constant cancels on both sides. Is that clear? Okay, so if there is any questions about that, you can ask again. So let us say that this is the number of people with age j. Okay. Now, obviously, if I sum over all such numbers, I get the total number of people in the room. Okay. Now, if I pick out one guy at random, the chances that I will pick out somebody with age j, the probability of picking out j is the total number of people with that age divided by the total number of people in the room. Okay. So this is equal to n of j divided by the total number of people in the room. So obviously, if I sum over the probability of finding the number of people with age j over all possibilities of j, I will get 1. Okay, why? Because this is equal to sum over j, n of j divided by sum over j and j. Now this is just a number that is independent of nj. So this is basically sum over j, n of j divided by sum over j, n of j, which is equal to 1. So the total probability always has to be equal to 1. Okay. Now, what is the average value of j? What is the average or mean age? What is the average age? They invented a new spelling for age. Age of people in the room. Okay. Now, whenever you want to compute the average of any quantity, so I will denote this average by a symbol like this. Okay, two angular brackets. This is the average value of the quantity j. This is equal to the sum over j times the number of people with that particular age divided by the total number of people. Okay. But I can write this as sum over j n of j divided by n. And n of j divided by n is nothing but the probability of picking out a guy with age j. So I can write the average quantity j as sum over j times the probability of picking out j. Okay, this is the average value of the age of people in a room. Similarly, the average value of the square of the ages, which will turn out to be important for some weird reason, which we will discuss in just 2 minutes. The average value of the square of the ages is if you follow the mathematics exactly, this will be equal to obviously j square n of j divided by n. Doing the same manipulation, you will find this is equal to j square times p of j. And you can carry this through for any function of j square, j cubed, 2j plus 1, e to the j, whatever it is. The average value of any function of j is the sum over j function weighted by the probability. Okay. This formula is very clean and it actually very nicely generalizes to the case of continuous distributions also, which we will talk about when I talk about function spaces. Notice a very important quantity. The average value of the square of the ages in general is not equal to the average value of the age quantity square. Okay, this is important to understand. Because these are two different quantities that you are taking the averages of. Okay. Now, usually we are happy to think of this average quantity as a very good measure of the kinds of population we have, right? So suppose if we have a classroom, so suppose if we have a random collection of people, let us say, okay, I ask what is the average age. The average age is a very good measure of the distribution of people that are there. Okay. But let us say, for example, if I'm talking to this class, suppose if you are all actually in a classroom, if this COVID were not there and I'm teaching you in a classroom, and I ask what is the average value of the age of this class, again, you can give me a specific number. But this population is very different from a very general population. Why? So if I take a very general population, and let me use a different color here. Okay. So let us say I plot the number of people with some j, some age j. So I'm plotting n of j against j. Okay, this is what is called a histogram of the population. Now, in a general population, I can get somebody with age 3, some 2 people with age 4, some 7 people with age 2, whatever it is, like this, right? One guy with this age, 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 whatever it is. There could be a spread of the number of people with some age j, right? Okay. Now, what if I do it for an MSc classroom? Now, in an MSc classroom or a BSc classroom or a combination of both, people are clustered together in ages, right? So suppose if I plot your ages as a function of j, I would find that the chance that, I'll find a person in your class with an age of 57 is almost zero. Because all of you belong to a certain age group between, say, I don't know, 21 and 25 or something like that, right? So suppose if I plot your ages, n of j against j, I can get a distribution that looks very different. So I will get somebody with, let us say, 21 years, somebody with 22 years, and a whole bunch of people with, let us say, 23 years, and let us say one guy with 24 years, and whatever it is, right? So something like this. Okay. Now, let me make an assumption. It is very possible that the average value here and the average value here is the same. Why? Because here there is in case 1, in case A, there is a large spread of the ages, right? So I have one guy with 21 years, one guy with 22, one guy with 23, one guy with 25, one guy with 32, 37. I can keep extending this. And let us say that I take the average of all these ages and I get something like 25. Okay. So let us say that in the first case A, the spread goes from age 15 to age 35 in some uniform fashion so that the average is around 25. In the second case, the average is also 25, but most of the people are age 25. So the difference between the distribution A and distribution B cannot be captured by just computing the average age of the population. If I simply say that the average value of age of this population is 25, it will not give me sufficient information to distinguish between the population type in A and the population type in B, because in population type A, there is very young kids and very old people, and the average is, or maybe not very old people, very young kids and people approaching middle age, but the average value is 25. In case B, there is no young kids and no middle-aged people, but all of them are around the age 25. They're all clustered together around the mean. So simply giving me the average value does not help me distinguish between these two cases. So I'll have to invoke some other mathematical measure by which I can distinguish the population type A and population type B. Okay. The most obvious choice is I will define some deviation from the average, delta J. So this delta J I will define as the age minus the average age. Okay. Now in the first case, delta J can be positive or negative, or maybe for one or two cases, 0. Why? Because for the first case, the average age is, let us say, 25, but there is a whole bunch of people with ages 15, 16, 17, 18, 19, 20. And there is a whole bunch of people with ages 27, 28, 29, 35. So delta J, which is the actual age of the person minus the average age, can be both positive and negative for the first population. For the second population, delta J is mostly 0 for the entire population, right? There is a few people with delta J negative. There is one or two people with delta J positive, but most of the people are at the median average age. So delta J would be 0. So this delta J seems like a decent measure, but there is a problem in using this delta J as a statistical measure. As a statistical measure, you always want to take the average value of any measure, right? The problem is if you compute the average value of delta J over this entire population, because I can see if there is like 2,000 people in a room, I cannot go around calculating delta J for every single guy. So if I want some way of distinguishing them, I want to have some measure of an average of this quantity. And it turns out that the average of this quantity is actually 0. Why? Because the average of delta J is the average of J, and the second quantity, which is, oh my gosh, this is not showing up. Sorry. I will stop share and share again. Okay, so this is what I mean. Delta J, which I define as the actual age minus the average age, but the average of this quantity is 0, because the average of this quantity is the average age minus the average age, which is equal to 0. So delta J, which seems reasonable to use, is actually not a very good measure to use in the theory of probability. So what can I do? It turns out that even though delta J is not a good measure, the average value of the square of this guy is actually a good measure. Okay, so I cannot use delta J, excuse me, but I can use delta J square. And this average value of this guy is, what is the average value? Again, average value is always equal to the quantity that I'm computing the average of weighted by the probability distribution, right? So this is equal to J. Delta J square is J minus average value of J whole square P of J. This is equal to J square plus average value square minus 2 times average value times J P of J. Okay, notice that these things are numbers, right? They are J independent. So this is equal to, the first term is j square p of j. The second term is plus j square, which I can pull outside, that is j independent is just a number, times sum over j pj. The third term is 2 and average value of j are numbers. This is equal to j p of j. Okay. So if I need to stop and repeat anything, please let me know as soon as possible. The first term is j square p of j, which means that is simply the average value of the square of the ages, because anything multiplied by the probability distribution summed over is the average value of that particular quantity. The second quantity is basically just j square, because sum over j pj, this quantity, the total probability is equal to 1. The third quantity is minus 2j times sum over j, jpj is another factor of average age. So this the average of this quantity delta j square is equal to j square, average quantity of j square minus average quantity of j the whole square. Okay, this is a very important measure statistically. This can tell me how a given population varies in age. So what does this mean in the context of our example? In the context of our example, the average value of j square minus the average value of j the whole square for population type B would almost be equal to 0. Okay. For population A, it will not be 0. For population A, the average value of the change of a particular guy's age minus the average age, the whole square of this quantity, is not equal to 0. So this quantity, even though the average age cannot distinguish cases A and B, this quantity, this weird quantity that we have discussed, the difference in the average, the difference between the age and the average age quantity squared's mean quantity, this quantity can indeed differentiate the two populations. And this quantity is a very important quantity. And as you might know, this has a name. This is called the standard deviation. This is called the variance. The square root of variance is called the standard deviation. It's called the variance. Okay. And square root of variance is called the standard deviation. Now, why am I going through all of these cases? Sorry, somebody is asking, sir, can you explain how the quantity helps to differentiate the two systems again? Very good. So let us look at the two systems again. Both of these systems have the same average age. Okay. Now, if I calculate delta J for population A, and if I calculate delta J for population B, what will I get? See, I want to understand how much the general population differs from the average, right? Now, in the case of the first example, the average value of this quantity delta J would be equal to 0. Why? Because there will be as many number of people below the average age as there are people above the average age. Okay, so if I average out this quantity for this population A, it will be 0. For the population B, again, this will be 0 because most of the people correspond to the average age, right? So if most of the people correspond to the average age, then delta J for each one of them will be 0. So the sum of them will also be 0. So for delta J, even though it looks like a reasonable measure, it's not actually a good measure because it turns out to be 0 for population A and population B both. So we use what is called the square of this guy. The square of this guy is delta J whole square. Now what happens to delta J whole square? Delta J whole square is the average value, so let us actually write this down here so I can explain this. So j square minus j whole square. Okay. Now, what will be the variance in age measurement for the cases A and cases B? For case B, what will be the variance in the age measurement? Well, since most of the ages are the same, for the case B, you can easily satisfy yourself that the average value of the square of the ages would be equal to the average value of the age quantity squared. Okay, because all the ages are approximately the same, the average value of the j square will be the square of the average value of j. For case A, that is not true because there's a wild difference in the individual values of delta j. Okay, since there is a wild difference in the individual values of delta j can be, for one guy, delta j could be minus 47. For another guy, the delta j could be minus 23. For a third guy, the delta j could be plus 17, whatever it is. Okay, so for the population A, this quantity, the variance, would not be equal to 0. Okay, so variance is actually a good measure of differentiating these two populations, even though delta j itself is not a good measure of differentiating these two populations. How is it relevant in quantum mechanics? In quantum mechanics, this is relevant for the case 2 that we are going to discuss. So the case 2 that we will be discussing, oh my gosh, so it's again not showing up, so I will share the screen again. Sorry about this. I need to buy a new iPad. Sorry, I need to buy a new computer. Okay. So, case 2, the two operators A and B do not commute. A, B do not commute, which means A comma B is not equal to 0 and they don't have a common set of eigenkits. So what do we do then? So let us define the average value of the operator A and operator B. Just like we defined an average age, we have to define the average value of A. Now, what does this mean in quantum mechanics? This means that I'm defining the average value of the measurement of A in some state psi. So this is, I will define this as A psi. This is the average value of A in state psi. How do I interpret this quantum mechanically? Remember that quantum mechanics is a probabilistic theory. So the way I understand this is saying that suppose, now one of the postulates of quantum mechanics, which we will come to, is that all the observables in classical mechanics are replaced by operators in quantum mechanics. Okay. So when I say the value of an operator, I simply mean that what is the value of the experiment that you will get when you try to measure this observable. Okay, we will talk about this in more detail. If this is a little confusing, don't worry about it at this stage. This also has another name in quantum mechanics, which we will employ commonly. This is called the expectation value of the operator in the state psi. Okay, this is nothing but the average value of the corresponding observable. Again, I will measure the change in the observer value from the average value. Just like I measured delta J, I'll measure the change delta A and delta B for two operators. Okay. All right. Now, if two operators do not commute, now what is formally delta A? Delta A in quantum mechanics, of course, unlike in the case of simple H's, delta A itself does not have a meaning. Again, delta A should be understood as delta A acting on some state psi, which is A minus A acting on the state psi. Okay. So this is some vector alpha. Okay. And then delta B acting on psi is again B minus the average value of B. This operator acting on the state psi. This could be some vector phi. Okay. There is something called the Schwartz inequality that you will study in your mathematical physics course, which I will not derive here at this point because it is actually quite, the proof of this is very common, and you can find this in any book on linear algebra. For two vectors alpha and beta, so let us call this some vector beta instead of phi. Okay, Schwartz inequality. States that the square of the length of alpha times the square of the length of beta should be greater than or equal to the overlap alpha beta whole square. Okay. Now this looks rather very mysterious, but if you translate this in the language of usual vector algebra, it is not at all mysterious. Let us say that you have two vectors A and B. Okay, if you have two vectors A and B, okay, now the square of the length of A is basically A square. The square of the length of B is basically the length of the vector B square, and the overlap alpha beta corresponds to the dot product A dot B, right? So if I want to make a correspondence with your usual vector analysis, this would be the correspondence, right? Now you know from ordinary vector calculus that A dot B is the length, the square root of the length of A times the square root of the length of B times the cosine of the angle between them. Now I can rewrite this relationship as cosine theta equals A dot B divided by B. Okay. Or cosine square theta equals A dot B. A dot B square divided by A square B square. I'm squaring the relationship. But cosine square theta is an angle which has to be less than or equal to 1, right? Cosine theta cannot be more than or equal to 1. So this tells you that A square times B square has to be greater than or equal to A dot B square. Okay. So the generalization of this in the case of linear algebra, generalization to LVS is if you have a vector A or a vector alpha and a vector beta, then the square of the length of alpha times the square of the length of beta should be greater than or equal to, not alpha dot beta, but the overlap alpha beta. Now, since this is a complex number, in this case, I will take the absolute modulus because the left-hand side is a manifestly a real quantity. So this is the generalization in the case of linear vector space. Okay. Now I can use this relation and the fact that delta A acting on psi is alpha and delta B acting on psi is beta. So instead of alpha beta, suppose if I use alpha equal to delta A acting on psi and beta equal to delta B acting on psi. Okay, so substitute alpha as delta A psi and beta goes to delta B psi. Okay, then this relation, the Cauchy-Schwartz inequality, can be written as, I'll prove this in a tutorial problem, delta A delta B is greater than or equal to 1/2 times, and there is a lot of brackets here, now this is a very, very important relationship called the uncertainty principle in quantum mechanics. So we will discuss a little more of this in the tutorial problem. Okay, what this means, the physics of this equation is as follows. Delta, remember that the left hand side is not an operator. Okay, it is just a number. Delta A means the uncertainty in the measurement of the quantity A. Delta B means the uncertainty in the measurement of the quantity B. The uncertainty in the measurement of quantity A times the uncertainty in the measurement of quantity B has to be greater than or equal to some minimum value. This minimum value is proportional to the average value of the commutator of A and B. So what is the physics of this equation? If the operators A and B commute, then the right hand side is 0, which means the uncertainty in the measurement of A times the uncertainty in the measurement of B can be equal to 0. But if two operators do not commute, then the corresponding uncertainty in the measurement of A times the uncertainty measurement of B can never be equal to 0. Which means no matter how wonderful the experimentalist is and how carefully she fine-tunes her apparatus, there will always be some finite uncertainty upon her measurements imposed by nature that she cannot possibly circumvent. Okay, this is called the uncertainty principle. We'll talk more about this as we progress in this course. This is a simple result of two operators not commuting. Okay, AB minus BA not equal to 0. This has led to Heisenberg's famous uncertainty principle and all the associated silly jokes in the internet about this. Okay, we will stop here at this point. I promise this will be a short lecture, but I took up the entire time. I'm sorry. We'll stop here at this point and we will take this up further tomorrow. And then tomorrow, after this short discussion is done, I will also start talking about the postulates of quantum mechanics. Okay. In fact, I will start talking about the postulates of quantum mechanics and then come back to this. I think that might be a little more effective in making you understand what this is all about. Okay, so that is the plan for tomorrow. Are there any quick questions about any of the things that we discussed? Does that mean to the measurements of two quantities being done simultaneously, right? Yes, it is two quantities being measured simultaneously. So I will talk about this in more detail once I introduce the measurement postulate in quantum mechanics. Of course, I can measure A and then go back to my room, have a cup of coffee, come back and measure B, and I will get accurate values of both. That is not what I'm saying. If I try to measure both at the same time, yes.